Hello once again, this is the Pencrest High School AP Physics C video series. This is video 1E, Quantitative Graphical Analysis. So now what we're going to see here is how graphical analysis and mathematical kinematics can lead us to the same conclusions. What you see here is a table of velocity versus time data. What we're going to do is use our calculators. We're going to use a function called quadreg to determine the function of velocity versus time. You'll find it under the stat and calc menus in your calculator. You'll have to put the data into lists first before you execute quadreg. Function will generate the following function: v equals 0.1816 t squared minus 4.6322 t plus 22.506. Yours should be similar. If it's not, it means you have the lists in the wrong order. So now when we graph that function, again, you can use your calculator to graph L1 and L2. It should look a little like what you see below. Now, we'll notice the qualitative characteristics first. Based on the shape of the graph, it's clear that the object is initially moving to the right and slowing down. That's this portion here. We can see that the curvature of the graph is positive, like a bowl, which indicates the positive jerk term that we see up here. We can see the local minimum, where the graph is at its lowest point. We could also call that the maximum negative velocity, somewhere in here between 12 and 13 seconds. If we look a little more closely, we can see that the velocity, the graph crosses the time axis twice. Once here, between 6 and 7 seconds, and then once here at about 19 seconds. So what we have is 4 different types of motion in this graph. The first interval, which ends as the curve crosses the time axis the first time, is plus minus a with positive jerk. It's moving to the right and slowing down at a decreasing rate because the magnitude of the acceleration is getting smaller. At this point in time, it stops briefly, and then it begins to speed up, moving to the left at a decreasing rate until about 12 or 13 seconds. At this point, the slope would be 0, so there would be no acceleration briefly. Then it begins to slow down, still moving to the left but slowing down. Notice that the acceleration term and the jerk term are both positive at this point. It slows down until about 19 seconds. It stops again, changes direction, and begins to accelerate to the right with a positive jerk term. Now, quantitatively, we can approach this just as we did with the given velocity function in the previous section. We can see that the 2 points in time when the object changes direction are 6.53 seconds and 19 seconds. Again, we would take this velocity function and solve for the zeros. The point at which the acceleration is 0, if we take a derivative of the velocity function and find the acceleration function, we would find that the acceleration is 0 at 12.8 seconds. Again, these match up well with our initial visual inspection. So now if we assume that the initial position is at the origin is at 0, we could integrate this function and we would find that the graph looks like this. In the event that you needed to sketch the graph, you wouldn't need all these points. You would need the initial position, and then most importantly, the two positions where the object changes direction. So again, going back, we already know from the velocity graph when the object changes direction. We could then plug those values into the position function, find out where it is, and graph those 2 points, and then perhaps one more to the right here. The acceleration versus time graph. Again, we know from the velocity function it stops at t squared. The degree of the polynomial is 2, so there is no additional term, which means that the jerk is constant. We have a straight line. We know the initial acceleration from this term here. Remember, it's plus a naught times t. So here's my initial acceleration. That's right there. We could use the acceleration function to find out when it's 0. We would find again that it was 12.8 seconds. So that's right here. Connect those 2 points and extend the straight line to the ends of the graph. Okay, so that's quantitative graphical analysis. You will have an individual assignment to work on in class where you will need to execute the quadreg function and figure out what the velocity function is for your particular data, and then do various analyses like we've just shown, including sketching the graphs. Okay, next up is vector analysis. We're going to extend vectors from 2 to 3 dimensions and look at some new vector operations. Until then, enjoy. I'll see you again soon.